Hi, everybody. Welcome back to another segment of some statistics here. In this next segment, we're going to talk about how to incorporate something known as the student's t-distribution to deal with the reality that we may not know the population standard deviation, and hence we would have to estimate it. So we're going to construct a confidence interval using a slightly different distributional assumption than the standard normal assumption. So this is a little bit of a departure from what we've been doing. So in this situation where we do not know the population standard deviation, we're going to estimate it from our data. And we're going to go ahead and exploit the distribution known as Gossett student t-distribution in order to construct our confidence interval. And everything is going to work very, very similarly with a few small differences. So you'll notice in our formula here, instead of the z-score value, we have this t value that we're going to be looking at. So we're going to use a different table, and you guys should have access to this table in the course materials in the table folder. S, the estimate of the population standard deviation, right, is going to be replacing sigma in the formula. And the square root of n shows up in the same spot just as it had done before. Now, the important thing to know about a t-distribution is as the number of observations gets larger, the t-distribution approaches a normal distribution. Okay, so if we had a standardized distribution, meaning it's centered at 0, here is what a t-distribution looks like. You might be wondering, what's that df equals 5? That's actually related to the sample size. So the one thing that's important to realize here is the shape of the t-distribution changes with what are known as the degrees of freedom associated with the distribution. And for our purposes of calculating a sample mean, the degrees of freedom is just going to be equal to n-1, the sample size minus 1. You'll notice if the degrees of freedom increase, the t-distribution starts hugging around the center a little bit more. The dispersion starts to shrink. And if we were to increase the degrees of freedom towards infinity, then this thing starts to approach a normal distribution. So in general, the t-distribution, it is a type of bell-shaped symmetric distribution, but it has slightly different kurtosis. It has slightly fatter tails than the normal distribution. And again, the way we're going to calculate the degrees of freedom is pretty simple. You're just going to take your sample size and you're going to subtract 1. Okay, so hopefully you all have access to that student's t table that is in the folder with the other tables, the normal table, binomial table, et cetera, that we've looked at. And it should look something like this. I don't have all the table displayed here, but we have the part of it that we need for this problem, where we're going to think about how do we find the relevant t value given a particular sample size and given a particular confidence level. Now, if you look across the top rows of this table, it tells you right away for different confidence levels. And that's defining for us which column we should be looking down. So if I have to make a 95% confidence interval, I'm going to go right here. And you'll notice 95% confidence interval corresponds to an alpha level of 5%. So that's in this two-tail row. And half of that corresponds to 2.5% probability being left in one of those two tails. So in this problem here, n is equal to 3, which means our degrees of freedom is going to be equal to 2, just n-1. And we're going to be interested here in looking at a 90% confidence interval, which means we're going to set alpha equal to 10%, so that alpha over 2 is 0.05. So you'll notice we could look at, if we're looking for a 90% confidence interval here, the alpha value is 10%, that's right here, and our alpha over 2 is 5%, the one-tail probability. And the question is, what is the t value associated with this particular confidence interval, right? We've locked in an alpha over 2 value of 5% in the upper tail, also 5% in the lower tail, but again, we're going to just use the one-side treatment here. So if we have 2 degrees of freedom, I'm going to now move to the row of this table associated with exactly 2 degrees of freedom. Okay, and then I'm going to find the relevant column, which is associated with the level of confidence that we're interested in. So if we're using an alpha of 10% of 0.1, that corresponds to a confidence level of 90%. And this then pins down a t-value for us of 2.92. So the way to interpret that is if we wanted to construct a 90% confidence interval with only 3 observations, okay, then 90% of the data with only 3 observations under the t-distribution falls about 2.92 standard deviations away from the center of that distribution. So if I go 2.92 standard deviations to the right, 2.92 standard deviation to the left, that would define my upper and lower bounds using this particular t-distribution. Now, if we were to think about how does the t-table compare to our z-values? Well, if I show you the full table here, we can see a little bit of a difference, right? In fact, if I had 30 degrees of freedom and we were using a 90% confidence interval, we would be using a t-value of 1.697 standard deviations, or standard errors from the mean. You'll notice, though, as n goes to infinity, okay, this number is close. It's not exact, but it's close to the number that corresponds to the normal distribution at the 90% confidence level. And if you go back to the first segment on interval estimation, you should see that for the 90% level, which was a very commonly used, confidence level corresponding to the 10% level of significance. This gives us a value of 1.645. Okay, so the t-distribution, it does approach a normal distribution, meaning the t-table looks more and more like the z-table as the degrees of freedom approaches infinity, as n approaches infinity. Let's go through a couple more exercises just to make sure we're comfortable using this table. So next question here, pretty straightforward. We want to find the t-value for an alpha over 2 for a tail probability of 2.5% with 15 degrees of freedom. Okay, 15 degrees of freedom means we're dealing with a sample of size 16. Recall the degrees of freedom is equal to the sample size minus 1. So to figure this out here, we're going to go down to the row that corresponds to 15 degrees of freedom. And hopefully you realize that the confidence level we're going to be dealing with, if there's a 2.5 probability left in one tail, that means there's 5% probability in both tails, meaning we're using a confidence level of 95% probability. So the best answer choice here is absolutely choice C, which corresponds to a t-value of 2.131 standard errors or standard deviations away from the center. Okay, if we were to change the question a little bit, let's find a t-value for an 80% confidence interval for a sample size of 16. Okay, again, we're given this information, right? So now I'm going to be using the first column of the table. First column corresponds to this confidence interval up at 80%, confidence level at 80%. But we have a sample size of 16, which means we're going to use our degrees of freedom here, n minus 1, which tells me, again, I'm looking at the row according to 15 degrees of freedom. And now we're going to go to that first column corresponding to the 80% confidence level. And we can see here now that this corresponds to 1.341 standard errors on either side of the center of the t-distribution. Okay, another example. We'll do a couple more just to make sure we are painfully comfortable utilizing this t-table. We want to find a t-value for a sample size of 36, assuming a 99% confidence interval. So 99% confidence interval means we're going to use this far right column over here. And if we have a sample size of 36, that means we're going to have 35 degrees of freedom. So we go down to that row, go to that far right column, and we can see, boom, we have a t-value of 2.724, which is choice D. You'll notice if you look down that table, it looks like the degrees of freedom kind of makes a big jump from 60 to 100 to 800 to infinity. So for this course, if you have a sample, that's bigger than 800, if you have a sample of like 1,000, for example, we're going to go ahead and just use that bottom row of the table here in this case. Okay? And if we wanted, again, to construct an 80% confidence interval using 1,000 observations, I go to that bottom row, I go to that first column, and this tells me I want to use a t-value of 1.282 standard errors from the mean, which would be choice A. If we had a sample size of 5 and we wanted to make a 90% confidence interval. Okay, then again, same drill here. Sample size is 5. That means we're using 4 degrees of freedom now. Okay, so I'm going to go to that row number 4 for 4 degrees of freedom. I'm going to go to my 90% confidence level column, and that tells me we should use a t-value of 2.132. Okay, so let's go ahead and apply the t-distribution now to a situation where we actually need to estimate both the sample mean and the sample standard deviation in the case of the situation that we're going to look at here, which is a company trying to figure out its financial health in terms of its debt to equity ratio. Okay, a high debt to equity ratio indicates financial instability, and banks often monitor the health of their companies by looking at these ratios and deciding whether or not they want to extend commercial loans to them. So let's suppose, to reduce risk, the bank decides to initiate a policy limiting the mean debt to equity ratio of its portfolio of commercial loans to a ratio of 1.5. So that's what we're looking at here. In order to estimate that mean debt to equity ratio of the portfolio, the bank is randomly selecting 15 of its commercial loan accounts. So it is a sample of 15 different accounts. And they find that the mean ratio across those 15 accounts is 1.343. And the sample standard deviation that they've estimated here is 0.192. And what we want to be able to do here is calculate a 95% confidence interval for that sample mean. And the question is this point estimate of 1.343, is that actually lower than 1.5, or is that because we have some sample noise since we only selected 15 observations in the sample? So goal, let's calculate that 95% confidence interval. And the question is, do the bank's current commercial loan accounts comply with its new policy of keeping underneath that 1.5 threshold? So here's what we know. We're given a sample mean here, and we're also given the sample standard deviation. If we had the data on these 15 accounts, obviously we would calculate those ourselves. We have 15 observations, and we are using a significance level of 5%, or conversely, a confidence level of 95%. So this is what we know. And first thing we need to do here before we can plug and chug is we have to figure out what the associated t-value is for this situation. And first thing we need to do is calculate the degrees of freedom. If we have 15 observations, the degrees of freedom under the t-distribution is going to be equal to 14. So now what we need to do is figure out what is the t-value associated with a 95% confidence interval. So I'm going to go back to my t-table, which isn't shown here. So I want you to do this on your own. Maybe pause the video. Find that column for 95% confidence level. Find the row corresponding to 14 degrees of freedom. And if you want to pause the video, you can do that. Check your answer. And you should wind up with a value of 2.145 standard errors. Or standard deviations away from 0 in terms of the t-distribution. Once we've done that, life is fairly easy. We now have our estimated values of S, of X bar, we know N, and we now know T. So we can plug all these values right back into our formula, and we're going to compute the margin of error based on the t-distribution instead of based on the z-distribution, on the normal distribution. And when we do that, we wind up getting a margin of error of around 0.106, and we can add that to our sample mean and subtract it from our sample mean to construct our confidence interval now, which runs from a debt to equity ratio of 1.237 to 1.449. Okay, so the interpretation of this using the t-distribution is that the bank is 95% confident that the true mean debt to equity ratio for its portfolio of commercial loans is between this range of values. So based on this interval, the argument is there's fairly strong statistical evidence that the bank's current commercial loan accounts are in compliance with its new policy. At a 95% confidence interval, even the upper bound threshold of 1.449 is below that mean debt to equity ratio policy ceiling of 1.5. Okay, now, The t-distribution, this is important to use if you do not have enough observations to apply the central limit theorem. Okay, so again, as t approaches z, as n gets very large, sometimes it is appropriate to use an approximation. Okay. However, the technically correct way to do this is to use the t-distribution and to use your estimate. Okay, however, if n is large, okay, it approximates a normal distribution. The t-distribution is going to approximate a normal distribution, so you can get away with using the z-score here instead of using the t-value, okay, provided n is sufficiently large. So the question is, well, should I use z or should I use t? And the answer to that is, well, it kind of depends on which situation you're in. If you know your data is normally distributed, okay, and you know what the population variance is, use the z-table. Okay, we can also use the z-table even if we do not know what the population variance is, just like on this last slide here, right? We didn't know, so we estimated the population standard deviation here with S, but we still applied the Z value. Okay, so first situation, if we know what the population standard deviation is, and we're assuming normality of the population itself, use the Z table. Okay, otherwise, I may not know what sigma is. In that case, let's estimate it with S. As long as n is big, I can use the Z table just like we saw in the previous slide. However, if I do not know sigma and I estimate it and n is small, then I want to use the t-distribution. Okay, so we're going to pick up in the next segment discussing how to think about the optimal sample size. So we're going to actually reverse engineer the margin of error and think about if I wanted to reduce my confidence interval. Like suppose here's my confidence interval and I want to make it smaller. I want to have less uncertainty about my parameter estimate. One way we could do that, we saw earlier, was by increasing the size of our sample. So if we wanted to think about like cutting our uncertainty in half, I want to know how many extra data points would I need to collect? What's the cost on my data acquisition in order to reduce my uncertainty around a particular parameter estimate? And we'll pick up with that in the next video segment. See you soon.